Today we're going to talk about the alternating series error bound and the Lagrange error bound. So both of these are, if you're looking at partial sums to figure out, to estimate the infinite sum, how far is it from the actual infinite sum? So the first case is if you have an alternating series. Now this only works if you have a converging alternating series. So if the series passes the conditions of the alternating series test, meaning the limit of the nth term goes to 0 and it's strictly decreasing, then you can estimate the error, you can bound the error using the next term. So if you're, it gives us basically a worst case scenario for the estimate. So we're going to look at the alternating harmonic series here. And first thing we're going to do is add up the first four terms. So if we add these up, and you can use your calculator for this, we get a value of 5.5833. We know the alternating series converges from the alternating series test. We're going to look at, well, what does the harmonic series, alternating harmonic series converge to potentially? The maximum error, so we can write this in different ways. I'm going to say S minus S4. Okay, the difference between the infinite sum and the partial sum we just found must be less than the next unused term. So that's going to be A5 in this case. Okay, which would be, the next term in this would be 1/5. Regardless of if it's positive or negative, we don't really worry about that. So we know that the maximum that this value is off by is 1/5. So I can find an upper bound and a lower bound. Okay, if this is my estimate, my upper bound, the biggest that the infinite series could possibly be would be the value that we got for the partial sums plus 1/5, which is 0.7833. The lower limit, we're going to subtract 1/5, which would give us a value of 0.3833. So our sum is somewhere in between those two values. And how could we find a closer estimate? Would be to add more terms to our partial sum. So the more terms we have, the more accurate we're going to be. And it's just how accurate do you want to be? Okay, next we're going to look at sine of x. We're going to look at sine of x, which is centered at 0. We're going to look at 0 and values close to 0. We're going to look at the degree 3 polynomial, which is x minus x cubed over 3 factorial. And then we're going to add on another term and see how that affects our estimate. Okay, so for this, you're going to plug all these values into your calculator. So you're going to do sine from 0 to 1, the third degree polynomial from 0 to 1, and the fifth degree polynomial from 0 to 1. So here's our table of values. So at 0, all of them are pretty accurate. If we look at, these are our actual values. So 0.25, we're right on board. 0.5, this one's a little bit farther away, but the fifth degree polynomial is pretty close. Still pretty close, still pretty close. So there's two things. First off, the farther we are from the center, the less accurate our polynomial approximation is going to be. And the more terms we add, the more accurate our approximation is going to be. So we're going to use the alternating series error bound to find the error of sine of 0.5. So we know this is sine of 0.5 using this third degree polynomial. Well, the error, okay, must be less than the next term. Okay, which would be 0.5 to the 5th over 5 factorial, which gets us a value of 0.002604. So this is okay. but we can find better. The actual error between the function and sine of x. So we're looking at the actual error. So sine of 0.5 minus 0.5 minus 0.5 cubed over 3 factorial gets us a value of 0.002589. So the approximation for the error is actually pretty close to the actual error. So there's 3 zeros there. Okay, so we're going to find the maximum error in the approximation of cosine, this time, at 0.2. So we're using 3 terms here. The next unused term would be the 6 power 6 factorial, and we're going to plug in 0.2. So we've got 0.2 to the 6th over 6 factorial. And this one gives us 8.889 times 10 to the negative 8. So the error, if you were to type this in your calculator, you would have 7 decimal places before there was even a slight difference, which is pretty impressive. Next one, determine the degree of the Maclaurin polynomial required for the approximation of sine 0.3 to be less than 0.001. So sine is our odds. Okay, so we're going to just create a table here. You can organize it however you want to. So the question wants the degree. Okay, and then I'll look at the error, which is going to be less than the next term. Okay, so let's start with a degree 1. Okay, if I just said sine of x is x, the error would be the next term, which gives us 0.045, which is not good enough for us. We want to get less than that. The next possible degree would be degree 3. So I'll take this and plug it into the next term, which is that 5 term, which gets me 0.00002, which is definitely less than 0.001. So what we want is a degree 3 polynomial. Gives me that error that we're looking for, less than that. Okay, so let's take a look at an AP problem from the 2016 test. So the function f has a Taylor series about x equals 1 that converges to f of x in the interval of convergence. It is known that f of 1 is 1, f prime of 1 is negative 1/2, and the nth derivative after that is given by this equation. So we're going to write the first 4 non-zero terms and the general term for the Taylor series about x equals 1. Okay, so I've written out my template where we just need to find the 4 values in red here. The first 2 are provided for us in the description. So f of 1 is 1. F prime of 1 is negative 1/2. Okay, for these other derivatives, we're using this equation here. So I'll do this off to the side here. Okay, so we have negative 1 to the n, to the 1 in this case, or 2. Then we have 2 minus 1 factorial over 2 to the n. Okay, if we simplify that, we have a positive 1 factorial over 2 to the n, sorry, that should have been 2 to the 2, over 4. Okay. Okay, and then one more. So my third derivative is going to be -1 cubed. In the top, we're going to have 3 minus 1 factorial over 2 to the 3. So this will be a -2 on the top, because 2 factorial is 2, over 8. We're good here as far as the first 4 terms, but in order to come up with a general term, it may be helpful to simplify things down a little bit. Okay, so I did a little simplifying. Those are the same, that was the same. Here, I rewrote this 4 as 2 squared because that's how it got generated, and that's going to be useful. 2 factorial is just 2. Here, the 8 I put in the denominator as 2 cubed. 2 and the 3 factorial. 3 factorial is 3 times 2 times 1. So that would cancel to just a 3. So my general term, our series is alternating. So we'll have a -1 to the n. We've got x minus 1 to the 0, 1, 2, 3. So that's going to be the n over 2 to the n times n. We want to make sure that if we plug in, so to get this term, we'd have n was 0. So we're good on our alternating piece there. Okay, now that we have our Taylor series, it says we can use that Taylor series to represent f of 1.2 as an alternating series. So we're going to use the first 3 non-zero terms to approximate f of 1.2. Is approximately 1.2 minus 1 squared over 2 squared times 2. Since that is a numerical answer, we can leave it just like that. And then here's where our new piece comes in. We're going to show that the approximation is within 0.001 of the exact value. So our error is going to be less than the next term. So this is my next term. I'll plug 1.2 into that. Okay, we're going to hope it's less than this. We can do a little bit of work with this. Unfortunately, these questions are no calculator. So I'd have 0.2 cubed over 8 times 3, so 24. I could write 0.2 is the same as 1/5. So I could write it as 1 over, so 1/5 cubed would be the same as putting 5 cubed in the denominator times 24, which I'm just going to go ahead and say is probably going to be less than 0.001. Okay, our next example is from the 2022 exam. So we have a power series given to us with the general term. So part A, we're going to use the ratio test to find the interval of convergence for f. So in our ratio test, we do the limit as n goes to infinity of the absolute value of the nth plus 1 term Okay, so since these are going up by 2, the next term would be 2n plus 3. And same in the bottom. And then I'll multiply by the reciprocal, 2n plus 1 over x to the 2n plus 1. Okay, so we can rewrite this as x to the 2n times x cubed plus 1 over, rewrite this as x to the 2n times x. So the two n's will cancel. Okay, I've got x cubed over x, so that was reduced to x squared, and I can pull that out. Which leaves me with 2n plus 1 over 2n plus 3. So that means my absolute value of x squared, that limit is 1. So my open interval is -1 to 1. But then we need to check our endpoints. Okay, so we're going to plug 1 into our general formula. All right, let's start with -1. So we have -1 to the n, -1 to the 2n plus 1 over 2n plus 1. Combining these, we get -1 to the 3n plus 1 over 2n plus 1. Okay, which we could use a limit comparison test. Well, this is an alternating series. So alternating and it's harmonic. Okay, so that one's going to converge. If we plug in 1, we get -1 to the n times 1 to the n over 2n plus 1, which is -1 to the n over 2n plus 1, which is also alternating harmonic. So it is convergent. So our interval is -1 to 1, including both endpoints. Next it says, show that f of x minus 1/2 is less than 1/10. Okay, so we're going to use the alternating series test because this is an alternating series. This, my function value, minus 1/2. Well, 1/2 would be the first term if I just plugged in 1/2. So my error, using the one term, has to be less than the next term, which would be 1/2 cubed over 3. Which is going to be less than, this would be 1 over 24, which is less than 1/10. Okay, and then the C. Write the first 4 non-zero terms and the general term for the derivative. Okay, so we're just going to do the power rule here on all those terms. Okay, so derivative of x is 1 minus 3x squared over 3 plus 5x to the 4th over 4 minus 7x to the 6th over 7. And I'll deal with the general term next. Okay, because I can simplify this. So I have 1 minus x squared plus x to the 4th minus x to the 6th. So we have our terms that are alternating. And we have x squared to the n for our general term. Okay, then it says use the result from part C to find f prime of 1/6. So it doesn't say estimate, it says find it. Well, if you notice, this is actually an infinite geometric series with a1 of 1 and a common ratio of x squared. So what I can do is plug my 1/6 into that. And we do not need to simplify, we'll leave it just like that. If we don't have an alternating series, then we have another way to detect the error or bound the error is called the Lagrange error bound. So if this is the maximum value of the derivative, so that m goes here, we're looking at, let me define all these things. So this is my error. It's essentially the next, it's like the next term, right? Because this would be n plus 1 over n plus 1 factorial. But we have some pieces I want to define here. M is the maximum value of the nth plus 1 derivative for some C between your center and where you're evaluating. Okay, X is going to be our given value. Okay, A is going to be our center. So some things to think about with the Lagrange error bound. We're not actually finding the error, we're just bounding it, kind of a worst case scenario. We're still using the next unused term. We often overestimate the error because sometimes we often cannot find the maximum of this, so we kind of give it a bound. You will generally find that max value in one of three ways. Given a graph, you find something that's a clear bound. If f of x is sine or cosine, the max is going to be 1 because that's the biggest it could possibly be. Or you might just be straight up told what the maximum value is. Okay, so if I look at this, the function f has derivatives of all orders. We have a graph of the absolute value of f of 4, and we're going to, from a polynomial centered at 1, show that the actual value at 1/2 minus the third degree polynomial at 1/2 is less than 1/12. So we do not have an alternating series, or we don't know if it's alternating. So we're going to use our formula. Okay. So the error from the Lagrange error bound is the maximum value of the derivative. Okay, so we're looking at, here's 1, and here's 1/2. So I want to look at this chart and find the maximum between these two. So that's going to occur here. I don't know exactly what it is, but I know it's less than 30. So let's just go ahead and say worst case scenario, the derivative is 30. Then we have the difference between our center and where we're trying to evaluate, to the 4th over 4 factorial, because if this is P3, 4 is the next term. Not really sure what that number is, but we're just going to go ahead and say that's definitely less than 1/12. Okay, let P of x be the 5th degree. Now circle that because that's important. For a function about x equals 0. Information about the maximum absolute value of selected derivatives are provided between 0 and 1.2. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that f of 1.2 minus p 1.2 is less than k. So we're going to use the Lagrange error bound to find that value. Now what they give us is the 5th degree, 6th degree, and 7th degree. So we have a decision to make about which one is the correct one. If this is the 5th degree polynomial, we want the next one, which is 6th, to be my max error. Okay, we've got 1.2 minus 0. We're evaluating at 0, but our center is 0. If this is to the 5th, that's to the 6th over 6 factorial, which, this is a calculator active question, is 2.2438, which is C. Okay, this question is actually a calculator active question, which is interesting. So we've got some derivatives here. We're going to write the 3rd degree Taylor polynomial about x equals 2 and use it to approximate 1.5. Okay, so we'll fill in our pieces here. F of 2 is 3. F prime is 5. We're centered at 2. so there's my polynomial. Okay, so for my estimation, I can plug 1.2 in for x. Now typically I would just leave it like this, but we're going to need it for the next problem. So I'll go ahead and say that it is negative 4.9583. Okay, for part B it says the fourth derivative satisfies that the absolute value of the fourth derivative is less than or equal to 3. Use the Lagrange error bound on the approximation of f1.5 to explain why f of 1.5, the actual value of 1.5, cannot be negative 5. Okay, so using our error bound, our error is going to be less than the maximum value of the derivative okay, 1.5 minus 2. If we're using a third degree polynomial, our power here is going to be 4 because that's the next one. So 4 over 4 factorial. Using the calculator, our error is less than 0.00781. Okay, so the farthest that we can be away from this value is negative 0.0781. So what I'm going to do is take negative 4.9583 and subtract, because I'm trying to show that I can't actually get to negative 0.5. The worst case scenario is that we're 0.00781 away from that value. Okay, that is negative 4.966. That is the farthest that that estimation could be. So f of 1.5 cannot equal negative 5, because this is bigger than negative 5, and that's the farthest we can get. So that was the alternating series bound and the Lagrange error bound.